And so today we are going to talk about continue our discussions on the eigenvalue problem. Let's see, what do we have from the last time? So what do we have here? We talk about the, let me say, we have some linear algebra knowledge, and then we talk about the power methods, and then the power methods we have assumed that we organize the eigenvalues, eigenvectors in a way such that the eigenvalues and eigenvectors is in a descending way, and we get this one as the largest one, and it should be the only one largest numbers here. We assume this, so we have a strictly bigger than the lambda 2 here, and we also assume that we have a linear independent eigenvectors, and that is v1 to the vn, and so that we can express the x with the linear combinations of the vectors v here. So this is a linear combination, and later on, so I'm going to skip this part and then go to the derivations here. And I just briefly mentioned this last time. Stop. So it is going for down, and then it is going for down. And so here we have two cases when the lambda 1, the magnitude of the lambda 1 is very small, it's smaller than 1, and then this expression is going to 0. And then if this lambda 1 is bigger than 1, and then it's keep growing, this expression is keep going, and then it would diverge. And so what is the effect in the computer? So in the computer, if you remember, so what we have learned in the 104B, and then we have like 64 bits, 32 bits, single precisions, double precisions. And in the computer, it has only limited bits to store the information. Which means that if you are going too large, and then you don't have the computer cannot represent that number. If it is too small, and then the computer is not able to store the number as well. So it was just doing some not very good rounding up there, rounding down, up there, and then your calculations will become inaccurate. So the method is to doing some normalizations during this multiplications process. We just multiply the a in the front, right? But here we are going to doing some normalizations throughout the whole process. And let's say this is our initial guess x0, and we choose it as unit vectors relative to the infinity norm. You can you can decide another algorithm that is relative to L2 norm, L1 norm, and it's still the same methods, but you can choose different norm to normalize the vector here. And so here we choose the unit vector x0, which is relative to the infinity norm, and we choose a component from that x0, and then that component is with the index p0 here, and then that component is with the 1 value here, and then it equals to the infinity norm of the x0. And I have given out some example here. And last time we just finished the first part of the calculation. Once we do the normalization, and then we get the x0, and then to multiply by the A matrix, and then we got the y1. And then from the y1, we choose we define the mu1, and then what's mu1? It's just we get the P0's numbers index from the step 1, and then we take a look at this y1 vector, and then take out the P0's component from this vector here. And then we have calculated some things, and then calculate the mu1 is actually equals to this expressions. And this is the first iterations here. And then what's the y1? And then the y1 here is not normalized. So before we go to the next steps, we need to do some normalizations. And so next, let's go to the step 2. Step 2 here. Let's see, we have already get this, and then let me just move the examples to the below. Here, okay, good. And we already get the y mu1, and then so I'm going to give you a rough idea here first. So we are going to use the mu k to approximate the lambda 1. And your y value here, the y vector here, is going to approximate the v1, the eigenvectors. So we are going to do the iterations here. This is the only first iteration, and then we get the mu1. And let's see, and then let's take a look at the next steps. The next step is to, okay, so we already have the y1, and then we go to do the normalizations. But before we do the normalizations, we take a look, let the P1 be the least integers, or any integer you want, but here it's just give you a standard, and then get the least integers such that the yp1 for that y vectors, and then it equals to the infinity norm of this one. And then so this is the yp1, and so this is already the iteration 2. We have choose the next step. This steps p1 here, and then this p1 is the largest the least integer such that the number here, the component here, and then it equals to the infinity norm of that y1 vector. And then the y1 vector here, what is the y1? Y1 is just calculated here, and the iterations of efficiency rate. And then the iterations 2 here. And then it's just the ax0, a times the initial gas vector. And then that's my y1. And here I just take out the least integer such that it equals the y components absolute values equals to the infinity norm here. So next, I'm going to do some normalization. I'm going to do the normalizations for the y1 vector. And after I do the normalization, and then it's just we define it as the x1. So all the x here, and then they are normalized, they are unit vector in this algorithm. And x1 is just the normalizations of the y1, and then it's just the y1 vector. So this is a vector, and then divided by the yp11. And then what's yp11? It's just the y1 infinity norm. So it's just the yp11, and then it's just This one is just the y1 infinity norm. So if you take the x1 infinity norm, and then you will immediately get this. So wait a moment, this one is also equals to, I'm going to use the parentheses to write down this. It is equals to the yp11, and then what is the y1 again? It's the ax0. And if you take the x1 infinity norm, and then you immediately figure out that this is equals to the y1 infinity norm, and then if you take the infinity norm here, and then it equals to the infinity norm of the numerator, and then divided by this number, so it equals to 1. Does it make sense? This is the normalization process. Okay, you seem confused, so I'm going to write this down. And I'm going to use this to represent this is a vector. This is so confused there. The notations here are so confused. So x0 is the vector, and x1 is vector, x1 is vector. Okay, good. And so here we got this. What is the x1? The x1 vector's infinity norm, and then it equals to the y1 norm, infinity norm, and then divided by this number yp11, and then it's equals to this y1 infinity norm, because this is the definition here, the definitions of the p1 component. And so here we have this equals to the y11 norm, the y1 norm, infinity norm, and it equals to 1. Does it make sense? So now we have a normalized vector. And we are going to keep doing the calculations here. Before I move to the next one, I'm going to and also, so for here, you would see that which one is the largest value here in the x1 vector. In the x1 vectors, we have, because this is just a normalizations of the y1, and then you would immediately figure out that the yp11 equals to 1, and then it equals to the x1 infinity norm here. This is because xp1, the p1 component here is just a p1 component of the y1 and divided by this number. So it equals to 1. Any questions? So the p1 component of this vector, this is a vector. And then it's just the p1 component from this vector, and then divided by this number. And then so it equals to 1. And next, I'm going to do this step calculation, and then each step calculation is just multiplied by the A matrix. So I got this, I got the y2. The y2 is just the A times my normalized. This is the normalized vectors A1. And if you take a look at the definitions here, and then what is the x1? X1 here, if you take a look at the definitions, the parentheses here, and then we got this, and then if we write that out, and then we got A equal A times AX0 and then divided by the YP11. And so if we use the power the power of the matrix here to represent the A times A, and then it's just the A squared, X times the initials vector, P11. Okay, so I'm going to take a look at this. So the mu2, and the mu2 is just the mu2 here if you go back to take a look at the Y1, the mu1 definitions. The mu1 definitions is just the index from the previous step, and then it's just the largest component in the x0, and then this is the p0, and then we take the p0s, the p0 components of the y1, and then this is the yp01. And here we would do the same thing, but here we define the mu2, and then the mu2 here we define with the p1 index, and so we have the y2 and then p1. So if you take a look at here, p1 index is just the you would take the largest number. So that is the least integer such that this component equals to the infinity norm. That is the largest components in the y1. And so we have the p1 from here, and then we would go to define the mu2, and then that mu2 is just the p1 component of the calculations we saw here. So the index is a little bit complicated here, but let's see. We are going to calculate this number to see how this number, this mu k, is converging to the lambda 1. So next, we are going to calculate this number, and yp1, again, I'm going to rewrite this as the yp1 2, and then divided by the xp1 1. And because the xp1 1 is just equals to 1, and then it doesn't change anything, but let's write down the expressions here, and then you will see this. Let's go back to what we have at the very beginning. We have already analyzed this at the very beginning. So we do the multiplication here. This is the a squared x, and then it equals to, if we express the x in terms of the linear combination of the eigenvectors Vj, and then we do the multiplication here, and then it equals to the beta j. Beta j is just the linear combinations coefficient. Lambda j is the eigenvalues corresponding to the Vj. So I'm going to copy this down, but this time we have something different here. I'm going to copy this down. This is because we have a squared x on the right hand side here. So let's see. So why do I copy that down? Because we have the a squared x0 here. And then we just say we can write the x0s with the linear combinations of the eigenvectors, so that we can do the calculations as before. And then here is just taking the p1 components from this from this vector. So the calculation that should looks like this. So I just copy the calculations down, but here on the right hand side is still a vector. This is the linear combinations of vector, but I'm going to take the p1 component. So it equals to, I need to write down the p1 here, so that this is a number rather than a vector. And this is the p1 component. And let's see. And also we need to divide this by the yp11, because in the numerators we actually have something here. And next, let's calculate what we have in the xp11. And xp11 is just the, let's see, what's the xp11? xp11, and then it's just a p1 component from the x1, right? So let's see what is the x1. The x1 is just the ax0 and then divided by the yp11. I'm going to copy this down.
And then so that you would know what we are calculating. And because we are doing the component-wise things, and then we are going to take the P1's component out. And what is the AX0 again? AX0, and then the X0 here, we have already write it as the, this one is just the linear combinations of the beta j and then Vj. And then this is just the combinations of the eigenvectors. So let's go back to what we have in the calculations before. And then this is from the last class. And then let's see, we have finished this calculation here. If we write the x as the linear combination of the Vj, and then we can take the A into this expressions and then do the matrix vector modifications first. And then because it's eigenvectors, we have the lambda j Vj here. So I'm going to take this back to our calculations. And then we got this. This is just the multiplications by one A matrix. And then so we just have one A matrix here. And in the denominator, we should have, this means that in the denominator, we should have this. The AX0. This is the A times the X0. But now we are going to take the P1 component, and then which means that we can take the P1 component to the eigenvectors. And let's take the P1 here. And don't forget that we have divisions here. Divisions YP11. And what about the numerator? Numerator is this one. And now let's see. I'm going to do the same thing as before. I'm going to just extract the j equals to one item and out, and then keep the rest of things into the sigma sum. So let's see, what do we have here? We have beta 1 and then lambda 1 square. Because this is the divisions, and then this just cancel out. And then let's just focus on the sigma sum. And then this is lambda 1 square, and then VP11. And then doing the sigma sum here, n equals to j equals to 2 beta j lambda j square, and then VP1j. And in the denominator, we have beta 1, lambda 1, VP11, and then sigma sum, n equals to j equals 2 beta j, and then lambda j, and VP1j. And then now I'm going to extract the lambda 1 out, and then lambda 1 from the denominator, from the numerator, and then I got this. And then beta 1, let me see, and then I got this, beta 1, and then VP11, and plus this. Let me see. Actually, I'm going to divide the in. So first, I get one lambda 1 out, and then I also divide the numerator and denominator by lambda 1. So I just have beta 1 VP11 here, and then this here I have beta j and then lambda j square, and then but it's divided by the let me see the calculation here. It should be lambda 1 square, and then VP1j. And because I also divide the numerator by the lambda 1, and then in the numerator I have this beta 1 and then VP11, and then sigma sum and j equals to 2, and then beta j and then lambda j, and then divided by lambda 1, and then VP1j. Any questions here? here I just, so you can really in this way. So you can divide, extract the one lambda one out. And divide the numerator and denominators by the lambda one.
This makes sense, okay, so because I extract the lambda one out, and then so you need to divide the lambda one first by for the numerator. So here we have beta one, lambda one, VP11, and then plus this things divided by lambda one. But later on, we divide the numerator and denominators at the same time by the lambda one. So here, divide the lambda one again, divide the lambda one again, and then this is divided by lambda one, divided by lambda one. So at the end of the day, this one you have is just some things without the lambda one, but here you have the lambda j divided by the lambda one and the square. Does it make sense? So here, this is the calculation. It's very
long and it's very lengthy here, but let's go to the next step. So this is just a calculation of mu2. And then once you get the y2, you would go to do some repeated process here. And the repeated process here is you get the y, right? And then you are going to do the normalization and to prepare for the next step. And actually the iteration 3, you can put it into the iteration 3 as well. But you can do some normalizations here. You are going to pick the P2 be the smallest number integer with the YP2, 2, and then this number it equals to the infinity norm of the Y2. This is the Y vectors from the iterations. Sorry, I have a wrong iterations number here. It should be iteration 4. This is the next step, iteration 4. And then if we want to prepare the vectors for the multiplication, and then we need to do some normalizations for the y2. And then the y2 here, so we define the x2, and then by divided by the largest number in that component, in that vector, this is vector, divided by the largest component, and then that is the infinity norm. And we are going to divide the vector y2 and then by its largest component in magnitude. And then at the end of the day, and then this equals to, what is the y2? Y2 is just the ax1, right? And what is the x1? Ax1. And then ax1 is just the a times the ax0. The x1 is just the a times a, this x1 is just equals to the a times x0. And then there's another a here, and then we have another a here, which means that if we use the power to represent this expression, and then it's just the a squared x0 here, and divided by, also we have some normalization, yp2 and then yp1 here.
This is because this is not just the, this is the YP2. Let me see, I have something wrong here, right? Some wrong writing here. It should be Y2P22. This is because we have some normalizations throughout the process. And this one, the X1 here, we have some normalization from the AX0. The AX0 is divided by the YP11 here, this X1. And so this is the number, and then you can keep doing the calculations as above, and then doing the component wise analysis, and we would get this general expressions here. So if you keep doing the iteration and then keep doing the analysis, we would get such a sequence. So we are going to do a lot of some similar calculation, and then you'll find out the general rule here. The general rule here is we get a sequence. You can see throughout this generations process, we would get a sequence of the xm vector. And then these vectors are normalized by the infinity norm. So they are unit vector, and we have the ym vector as well. And then the ym vector is just the xm vectors, xm minus 1, and then multiplied by the a on the left-hand side. And we have a sequence of the value as well. And then this is the sequence of the scalar value. And then what is that? And then they are the mu m number. They are the mu m number, but if you take a look at the number, and then it's just going to the lambda 1. So first, what is the ym? Ym is just the a times the xm minus 1. And what is the mu m here? From the process above, and then you'll find out the general rule for the mu m. The mu m is just the largest numbers, not largest number, it's just a ym, and then you evaluate at the pm minus 1's, that is the pm minus 1 component of the ym, and it is just the lambda 1 and then beta 1 and then vpm minus 1, and then this is the pm minus 1 components for the v1, the eigenvectors. And in their denominator, we have the same thing, but in the numerator again, and then you will see this. You will find out the pattern above, and then it's just a lambda j divided by lambda 1, and then the number here, the order here, it should be the m order, and then beta j, and then vpm minus 1 j here, and this is the numerator. And then for the denominator, we have sigma sum n equals to j equals to 2, and then lambda j divided by the lambda 1, and then n minus 1, beta j, and then vpm minus 1 j. And this is the mu m vector. And from this step, and then we can also define the normalized vectors for the next iteration. And then it is just a ym, and you are going to pick the largest number from that ym vector, the largest, the component with the largest magnitude. And in this way, you can normalize the vectors here, get a unit vectors, and then it also equals to this number, ypkk. So let me just repeat what I just saying. If you take a look at the first situation, you will get the mu1, right? And then if you take a look at the order here, it's just the order 1. And then here, it's just the order 0 for the lambda j divided by the lambda 1. And we have a lambda 1 here. And if you go to the iterations too, you will see this. This one, we have, scroll down a little bit. We have, this is where we define the mu2, and then you will see this one is with the order 2, and this one in the numerator, denominator is with the order 1. And in front of this parenthesis, we have a lambda 1 here. So that we have a generalization here, and then we can conclude that we have such a pattern, and you would have for the mu m here, and then it's just the, this one is with the order m, and then this one is with the order m minus 1. Any question here? Do you find out such a pattern? There, the things here is, there's a lot of things here, but if you go back to take a look at the notes, and then you will find the pattern. This number is corresponding to this index here, and then this one is just the index minus 1. So now I'm going to do some limit here. Let us take the limit tends to infinity. And let me denote something here where the PM is the smallest number, smallest integer for such that. So that is the where the components achieve the infinity norm. The infinity alarm of the YM. This is the normalization process. So next, I'm going to do some limitations process here. And I would like to remind you of the lambda j and lambda 1 relations. So here for this sigma sum here is from j equals to 2, from j equals to 2. And let me remind you of this. The lambda j is smaller than 1, lambda 1. Or I'm going to write it in another direction. Lambda 1 is bigger than lambda j for j equals to 2 to the n. And this means that the lambda 1 divided by the lambda j divided by lambda 1 is smaller than 1 for j equals to 2 and to the n. And if we let the limit m tends to infinity, and then what can we get? We get, so if we let the m tends to infinity, and this is just something smaller than 1, and then times to the order of m, and the m is tending to infinity. So this one is going to 0. And this one is also going to 0, because this number is going to infinity as well. Does it make sense? This is because this number is smaller than 1. This number is smaller than 1, but the order here is tending to the infinity. This number is smaller than 1. This number is smaller than 1, but m is going to infinity. M minus 1 is also going to infinity. So at the end of the day, the mu m, if we let it to tends to infinity, and then we have just this item, and then divided by this item inside the parentheses. Because this one are going to 0. This one are going to 0. Does it make sense? Confused. I saw some confused space. Yeah.
As definition of those two data, some number there is bigger than this and the value of this 0.
You mean that when the m is going to infinity, then that number is going to 0, right?
Mm-hmm.
And then you mean
just part of the solution becomes
you mean the sigma sum, right? So here, because this is a finite sum, it is not an infinite sum here. If the component here is summations component here is going to 0, and then this is a finite sum, and then it's going to 0. It is not the infinite sum. If you're right, if this is an infinite sum, and then it could be sometimes it could be a finite number, the summation. But here we just have n component, and it's is fixed, the dimension is fixed. So we have just n component and then it's going to 0. So it's going to 0 for the entire things.
So this means that this one is going to 0. The whole thing is going to 0. And this whole thing is going to 0. And at the end,
We just have this and this in the inside the parentheses. And this one is the same as this one. So this divided by this one is just 1. And
which means that at the end of the day, the mu m, the limitations of the mu m, if we take the m tends to infinity and then the mu m is tending to lambda 1. And this is a conclusion. And there's another conclusion here. And then the xm is converging to the xm sequence. Xm m equals to 1 to infinity is converges to an eigenvector associated with that eigenvalue, associated with lambda 1, and which has L infinity norm, and then it equals to 1. So
this vector, this sequence of vector, the xm, is converging to the eigenvectors, and then this eigenvectors has the infinity norm, and then it equals to 1, and that's the unit vector.
And now I'm going to let you take a look at one example here, and then you will see why we are mentioning all this normalization process here. And I hope I can paste something here. It doesn't work. Why? Okay. Let me try that again. No. So if you go to take a look at the textbook, I'm going to join the Zoom from another portal. So I'm going to let you take a look at the textbook here. So that is okay. So I'm going to write this down quickly. So if you go there to take a look at the textbook, and then the textbooks would tell you where's the textbooks? Let me just pull that out. Dropbox. That's super nice. I haven't downloaded it. So never mind. So if you go to take a look at the textbooks, and then that examples here, and then if you take a look at the numbers there, and then they are just exploding. That numbers are just exploding. And let me see, could I give you some things to I'm not sure how to get this work. Do you see anything? No? Nothing? Never mind. Let's go back to what we have. Okay, so never mind. Let's go back to what we have here. So if you go to take a look at the textbooks, and then you will find an example there. The A is this number, -2, -3, 6, 7, And it's going to calculate its eigenvectors and eigenvalue, and it has the lambda 1 equals to 4 here, and then the V1 is just the 1 negative 2. If you take a look at the textbook, you can skip the calculations over there. But if you take a look at the textbook, this is the true eigenvalues for the lambda 1. This is true eigenvectors. If you keep doing the calculation and you just keep doing the iteration, ax0 and then ax squared x0 and then a3x0 here, is actually equals to, if you go to take a look at the calculation, and this number is just the -5, 13, and then this one is just a -29, 16, and this one is just a 125 and then 253. And in the number, for the number x a to the order of a 6 x0 here, and then you will see a very large number, and then this number is this one, 16381. So this is what we have at the very beginning. The lambda 1 is bigger than 1. The magnitude of the lambda 1 is bigger than 1. And if you keep doing the A matrix multiplication, and then your number is growing so fast. So if it's going to like 4 places here, 5 places here. So if you keep doing some multiplication here, and then the numbers are growing so fast, and then at some point, the computer cannot represent the numbers you have here. So this means that we need to do the normalizations throughout the process. I have shown you some calculations here, below here. I just let you to read this iteration, and then this is the iterations we use, the algorithm we design here. We use the normalization, and then we call this one as the power methods. We do the multiplications, but throughout the process, we are doing some normalization. Here is the normalization. Here we also do some normalizations here. This number should be okay, this is the component number. So I'm going to just let you to read this after the class, and I will also ask you to perform power methods algorithms on one matrix as well to calculate its lambda 1 and eigenvectors and its corresponding eigenvector. Okay, so the textbook has included one example, but that example is explaining that why we need the power methods. So class is over, and thank you. What's that?